Hey everybody. So today we're going to talk about circular motion. Uh, this topic appears kind of abruptly in your book. Um, so circular motion is section 5.2 through 5.4, if I remember correctly. And this comes right after we talk about friction. So it might seem kind of out of place, but it turns out that this topic is actually really crucial because it allows us to connect back to what we had been doing. So we talked about Newton's laws in chapter 4, and we had just talked about friction in section 5.1. And going forward, uh, we're going to talk about gravity in the next chapter, chapter 6. And it turns out that the idea and the math behind circular motion will allow us to connect these things together. So we're not going to be able to work problems involving gravity and some of those cool applications unless we get these circular motion relationships worked out first. So that's what we're going to do today. Um, so the basic relationship thing that I want us to consider with circular motion is if you have an object that's, I'll try and draw the best circle that I can here. If you have an object that's rotating in a circle, so you have some object here, um, that object will have a velocity that is tangent to the circle, and it will experience an acceleration that is directed towards the center of the circle. So I'll put that in a different color here. And I'm going to denote that A sub r for radial acceleration. So this is the radial or centripetal acceleration. And this r is to tell you that it's in the radial r direction. So the mathematical relationship that we're going to take advantage of is the fact that the magnitude of this centripetal acceleration is equal to v squared over r, where r is the radius here of your circle. So this is going to allow us to look into all different kinds of cool problems. So a couple things to be careful about with this. Um, don't think of this as v and the size of the circle causing the acceleration. Think of this as this is just a way that we can figure out the magnitude. So this relationship lets us find the magnitude. So I'll say it tells us the magnitude of AR. We need something else to cause the acceleration. And as you know, the cause of an acceleration is a force. So you need some force to cause AR. So I'll put it in our picture in a different color. So that force is going to have to be pointing in the same direction as the acceleration. So it will also point towards the center of the circle. And for now, I'll just call it FR. And it turns out that there's lots of different forces that can cause a centripetal acceleration, including friction. So this is our connection to the first section of this chapter. But before we talk about friction, let me give you a visual example. So in the example that I just showed you, the force that is providing the centripetal acceleration is tension, the tension in the string that's holding the object. So let me try and draw this. You have an object that's whipping around in a circle above your head. There's at the end of a chord. So there's a velocity that's perpendicular to the, or that's tangent to the circle. Put in our other vectors here. So there's the tension force that's in the chord. It's providing the centripetal acceleration, and the centripetal acceleration that's aligned with it. So a couple notes about this that I want to bring to your attention. So one thing is, notice you can be spinning this thing at a constant speed. In other words, the magnitude of the velocity can be constant, but the object is accelerating because it's changing direction. And this is, think back to Newton's first law. An object is going to stay at rest or continue moving in a straight line unless acted upon by a net force. So in this case, it's not moving in a straight line, it's moving in a circle. It's changing direction. So since it's changing direction, there's a force. And since there's a net force, it's accelerating. So this is kind of interesting because it's a little bit different than our intuition about an object accelerating, where we think of it speeding up or slowing down. In this case, the speed is constant, but it's accelerating because it's changing direction. The other thing that's kind of interesting about this is to think about, well, if this object is spinning around, what happens if your string snaps? So our intuition might tell us like, oh, it flies away from the circle. So you might think like, oh, does it fly this way? No, it does not. If the string were to snap, notice that the velocity is tangent to the circle, so it's going to continue to go in this direction. That can be a little bit sort of counterintuitive, or maybe unfamiliar on the surface if we don't think about the fact that the velocity is tangent to the circle. Okay, let's look at some other examples. Another example of a force that can provide the centripetal acceleration is friction. So perhaps a sort of familiar example would be if you're in a car and you're going around a corner. Try and draw a car here. So a top view here. Now this is R. Now in this case, you would experience the centripetal acceleration going around the corner, but the force that's providing that centripetal acceleration is actually the friction between the tires and the road. If you didn't have this, you would just continue in a straight line. So, oh, and just for being complete here, so the centripetal acceleration towards the center of the circle. So I mentioned this, and we'll work a problem or two that involves friction as another example of a force that can provide a centripetal acceleration, and it connects back to the first section of this chapter. So another force that can provide this centripetal acceleration is actually the normal force. And I'm sure you've encountered this on the freeway. So you'll notice, high speed turns are angled. They're not flat. And this is because this allows a component of the normal force to be pointed towards the center of the circle, and it provides that centripetal acceleration that allows you to turn the corner. So we'll talk about that example, and also, you can have a situation where you can sort of the extreme case of this is if you have like a cylinder. If you're going fast enough, you can ride on the inside of the cylinder, and we'll look at that problem as well. And that's sort of a combination of the normal force and friction, allowing, providing this centripetal acceleration. So there's some interesting problems. And where this is all headed is gravity. So once we've mastered working with centripetal acceleration, we'll talk about gravity as sort of the granddaddy of forces that can provide centripetal acceleration. And we'll get to that in the next chapter.